Wonderful. So thank you very much for coming back so orderly. It's my great pleasure to invite Dr. Mariana Popescu to chair the next session. Mariana is an assistant professor of digital fabrication at TU Delft and has been a significant contributor to the fabricator community for many years. Mariana is a computational architect and structural designer with a deep interest in developing innovative fabrication approaches and use of materials in construction. Her area of expertise is computational and parametric design with a focus on digital fabrication and sustainable design, which operates at the intersection of architecture and engineering. This intersectional expertise is applied in the research and development of novel material systems, particularly including knitcrete, which I think many of us from the Fabricate community are very aware of. So this is a material-saving, labor-reducing, cost-effective formwork system for casting doubly curved geometries in concrete using 3D knitting. Before joining TU Delft, she was a postdoctoral researcher at the Block Research Group at the Institute for Technology and Architecture at ETH Zurich. And she was involved in the NCCR digital fabrication, where in 2019 she obtained her PhD, which was nominated for the ETH Medal for Outstanding Dissertation. And these successes, I think, continue. Congratulations on receiving recent funding, like many in the room. We'll hear more about that just before lunch. But Mariana, please come and chair the next session.
Thank you, Phil, very much for that wonderful, wonderful introduction. It is a very great pleasure to be a part of such a wonderful community of fabricators, and it is even more so a pleasure to be here today and be able to chair this session. Specifically, because this morning we have 4 presentations that span, that are insightful and are dealing with very innovative topics. And they are all lined up under the umbrella of RECLAIM. These presentations span a large area of both materials and technologies and approaches, which do not only highlight current trends, but also help shape the future direction of our industry in that sense. So as we delve into these topics, we hope to shed light on innovative strategies, on practices in the world of sustainable design and construction. Just to give you a little bit of an insight into the 4 topics, we will explore the versatility of materials in circular design, the unique challenges and solutions in creating timber structures, the potential of mycelium-based composites, and advancements in 3D concrete printing. Without further ado, I would actually like to give the stage to our speakers. So our first presentation of the day is on Striatus 2.0, and it will be given by Alessandro Dell'Endice from the Block Research Group at ETH Zurich. The stage is yours.
Thank you, Mariana, for the nice introduction. So, hi, everyone. I'm Alessandro Dell'Endice. I'm a postdoctoral researcher at the Block Research Group at ETH Zurich. And I'm really happy to present you the Phoenix Bridge. So, Phoenix is a permanent 3D concrete printed unreinforced masonry pedestrian bridge, which was built in 2023 in Lyon in the Holcim Innovation Center. And this project is a collaboration between the Block Research Group at ETH Zurich, the ZA-DID Computation and Design Group, ZA-Code, and Incremental 3D and Holcim. This project starts from the key learnings of Striatus. Striatus is a similar 3D concrete printed pedestrian bridge we built in Venice in 2021 during the ECC Architecture Biennale. These 2 projects demonstrate once again the power of strength through geometry, connect it to other two concepts which are strictly related to strength through geometry. One is material effectiveness, so using the material according to its own mechanical properties, and circular construction, which is triggered by the application of the masonry logic to 3D concrete printing. Then this was done by using the latest developments in digital fabrication, specifically additive manufacturing, and so 3D concrete printing, and computational design. In particular, we used Compass, which is a Python-based open source computational framework for research and collaboration in the AEC industry. But the development of this project starts from the application of historical reinforced masonry principles to new structures. In particular, when we work with structural geometry, so you see all the columns on the left side, we could reduce the volume of our structure, and we experience lower stresses because we are working with funicular geometries. By working with compression-only structures, we can minimize the bending, and we can reduce the mass, and we can also use weaker materials, which usually correspond to a lower ECC, so embodied carbon coefficient in the material itself. Then the discrete nature of masonry directly triggers circular construction. So we can easily reuse, we can recycle because materials are separated. We can then repair, so it's a discrete structure. We can remove one element and replace it with a new one. The masonry behavior, which is, let's say, influenced a lot by stereotomy, it's solved by digital fabrication because we have a certain flexibility of creating shapes through additive manufacturing. And the 3D complexity of masonry is dealt with the computational design. So we could now work with the three-dimensional geometries, calculate them structurally, and we can build up an integrated approach from design to fabrication. So how we translated this in a 3D concrete printing structure? First of all, we built a discrete masonry structure working in compression, and we shaped the single components in order to have all the layers always perpendicular to the flow of forces. So you see the layers are not horizontal, but they are inclined, and they also have a different layer height in their development. This research is based on my PhD at the Block Research Group on structural assessment and design of reinforced masonry structures using discrete element modeling, and on the PhD of Vishu Bhooshan about shape design of 3D concrete printed masonry structure. When we worked with the first bridge Striatus, we actually blended these two research together, and we generated this really integrated approach from design to fabrication, where we started simply from, let's say, a JSON file containing a data structure, network, and 3D meshes, and then we expand this mesh. You see, we started with the skeleton on the top left. We expanded the mesh in 2D, and we use this mesh as a form diagram for the truss network analysis. So as you can see in this diagram, the structural analysis is interconnected with the design, and we always have feedback loop along the path in order to inform our design process. So after the form finding through truss network, we gave to this mesh thickness, we discretized the mesh, and we checked this through discrete element modeling analysis. So we understand what's the global equilibrium, the displacement capacity, and the load combinations. And at this point, we also introduced all the constraints coming from 3D concrete printing and from the material properties. And then finally, we checked locally with the finite element analysis in order to define the thicknesses of the layers and, for example, the stiffening scheme inside the structure. And we populated this JSON file with all the data for fabrication, for structural reports, and for the 3D printing, the robotic 3D printing of the structure. Now, after the first project, so after Striatus in Venice, we wanted to actually improve in a second iteration the first bridge. And we did that not only thinking to how we could improve in terms of transportability, maneuverability, assembly precision, but how we thought, how could we reduce the environmental impact in these structural typologies. So we worked a bit on these equations, so on the equation of the global warming potential. So we then decided to reduce single-use materials, for example, for the construction of the waffle, so the false work of the bridge. We wanted to reduce the ECC by using a lower strength concrete. And we increase the lifespan building a permanent structure compared to Striatus that was just for the Biennale. So I will now guide you through the different steps from Striatus to Phoenix, and I will list all the different features and all the comparison between the two. From a geometry point of view, we slightly increased the span, so the span is almost the same, but what we did, this structure, the Phoenix one, is much more shallow, so it's more suitable for a pedestrian bridge, so we could get rid of the timber steps, so we save already some material there. But on the geometry side, we also increase the number of blocks, so it's almost double. And by doing this, there are a lot of benefits. So first of all, we reduce the angle between the start and the end plane during printing, which can reduce the layer height variability. We could use thicker layers, which means larger aggregates, and also reduce cement contact in the mix. But more discretization means also that we could reduce local bending from a structural point of view in the single components. We also, in this case, integrated a balustrade, like a standard steel balustrade, so giving more transparency to the project. And we did that by inserting this steel T element in between the components, which is kept in place simply by the thrust flowing into the balustrade arches on the two sides of the bridge. From a structural point of view, we increase the global thickness of our geometry in order to increase the equilibrium solution space, especially for example, point loads or asymmetric loads, which are the, let's say, worst load cases for this type of structure. And locally, we also went from double layer printing, which could rise to some cold joints between the layers, to a single thicker layer running around the 3D printed components. And both structures were designed considering all the requirements from the Eurocode, so ULS, SLS, and they were all tested afterward with sandbags in different locations to check basically the deflections under certain loads. On the false work, we went from this continuous timber waffle with a lot of wood that we built in Venice to a different system with cassettes, which were integrated with commercially available DOCA elements, so these blue beams that you see around the components. So we could reduce by 50% the use of wood per square meter. And we also increase the precision during the assembly because we pre-assemble these cassettes with a few components on top, and then we lift them up on top of DOCA towers, which were placed along the skeleton of the structure. On the material side, this is an image of the disassembly of Striatus in Venice. And after disassembling all the components, we smashed these components and part of these particles here were used as new aggregates for the recipe of the new concrete. But not only that, so the development between Striatus and Phoenix concerned also going from a 90 megapascal concrete, so a high-strength concrete with the maximum diameter of aggregates about 0.6 millimeters, SAM2, to SAM3 concrete with the 50 megapascal, so we could reduce a lot also the environmental impact of the mix. Coming from 100% recycled material, we use part of the demolition waste from Striatus. We could increase the aggregates to 2 millimeters, and we actually use local sand. So it was a local sand closer to the plant where we printed the components. On the assembly side, we changed the strategy. So we decided to start from the middle. This is a bit unusual compared to, let's say, what is usually done historically on masonry structure. So we started from the middle, and we wanted to accumulate all the imperfection at the latest interface between the last block and the support. So you see here, we proceed from the middle towards the support on the right side, and then we fill the remaining gap with mortar at the end of the process. Finally, I want to show you just a few pictures of the project. This is right after the decentering. This is the structure before mounting the balustrade, so the handrail on top of it. You see the connectors coming out in between the balustrade arches on the sides. And these are a couple of more images in the Holcim Innovation Center in Lyon. And so to conclude, I want to show you this slide, which is showing the CO2 savings compared to Striatus. Of course, here we added the steel balustrade, which is also made of, let's say, components that can be disassembled, so it's not really connected to the building, so it can be reused. And we realized, let's say, later that there is a big contribution there about the joints, because we double the number of joints, number of blocks, but then we also increase the neoprene pads in between. So there is still, this is just to say there is still room for improvements in this process. And I want to conclude with this diagram, which shows how the implementation of our reinforced masonry principles together with 3D concrete printing is quite beneficial for circular construction. So in this project, we are using 3D concrete printing as a primary structure. So there are no cables, no reinforcement inside. So we can start with a low emission concrete. We could reduce material because we are using additive manufacturing. And thanks to the masonry principles, we can go through these loops, so we can repair our structure, we could reuse it, so we can disassemble it and move it somewhere else, or we can recycle, as we did going from Striatus to Phoenix. This is a 40-second video to show you the final results in Lyon. Assembly of the cassettes, and the assembly starting from the middle, going towards the end, towards the supports. Thanks for your attention.
Thank you very much, Alessandro, for the insightful presentation. It's really beautiful to see how one bridge turns into the other, and then that makes it a phoenix, rebirthed from the first one. We are going to keep the questions for the end of the session when everybody is together, but if there is any burning technical question, and only one that would be more fitting now, then we can allow for that. If not, I would move on to our next speaker, which is Paul Nicolas. He is from the he is an associate professor here at the Royal Danish Academy. So without further ado, please join us on stage.
Great. Thanks very much for that introduction, and also, yeah, it's a really great pleasure actually to share our research here with a real live Fabricate audience, and to do that on behalf of all the authors of our paper. So our paper describes ongoing research into future design, fabrication, and resourcing strategies for architectural biopolymer composites. It takes point of departure in architecture's ambitions and intentions to radically intensify and diversify the use of biogenic materials or biogenic resources within or to use their use as construction materials. There's many metrics, but increasing the quantity of biomass within our buildings, within the built environment, would or should significantly lower the embodied carbon of buildings. More importantly, perhaps also in the short term, it would also increase the quantity of carbon that they're able to sequester out of the atmosphere. But to be able to get anywhere near these very sort of positive impacts, we first need to consider where the sources of these materials might come from. And this raises critical questions of how we should do this within the carrying capacity of our and sensitivities of our local ecosystems. And particularly how we should do this without simply shifting the burden to another planetary boundary. So in the right there. So the region that we're in now, Denmark, southern Scandinavia, has a landscape that's about 70% agricultural. It's a fully utilized landscape that's cultivating feed, food, and energy crops. However, this same landscape and the same cultivation practices also generate substantial quantities of what are called second and third generation biomass. So this is the residues, the wastes, the cut-offs, the unused parts of first generation plants and trees, as well as uncultivated biomass such as seagrass. And this kind of biomass, it has cycles that are very, very rapid. So a few months to grow, a few months to decompose, and this is even quicker if it's burnt for energy return. So being able to create sort of new slow loops that redirect these waste materials into building elements would increase the overall quantity of biomass that we're able to use within building materials and building elements. It would also sequester their carbon for hopefully substantial periods of time, and it would also reduce pressures on other critical biomaterial resources. And then creating these kind of loops is actually seen as half of the solution space for circular design. But I mean, if you take a minute to read the diagram, you can actually see in there that in architecture, most of our thinking and systems for circularity and reuse are heavily weighted to the technical side, to technical cycles and to product-based thinking. And when we move over to the biosphere side of the diagram, things get much sparser, and there's a need and room for invention of how we create these loops. And what we argue in our paper is that if we're to do this, and as we begin to create these loops, we need to embed our approaches in some of the realities of waste biomass sorting and cycling, which are actually obscured or left out of a diagram like this, as it strips those resources and flows from their contexts. So the first of those realities is that many of these flows are not constant. And the resource flows are not, they may be there, but they may not necessarily be there or be abundant when you need them. The available quantities of biomass and biomass residues vary year to year as they're affected by unpredictable events such as droughts, heat waves, rains, diseases, or other competing uses that might suddenly assign value to that waste. A second challenge is that the properties of the materials are also variable. So, for example, the tensile strength of materials like hay, flax, or hemp residues can vary up to 30% based on local agricultural practice, soil nitrogen fertilization levels, sowing densities, as well as local climate dynamics. And then a third challenge is that once these materials have entered into our building cycles, it's easy to think that they should replicate the same kinds of cascades and cycles that we have set up for technical materials, and to forget that actually many of these materials come in with quite unique properties, and this gives us a way to open up new logics of for architectural circular design. So the materials and methods that we are describing in the article open up these issues through a focus on biopolymers, and particularly 3D printed, graded, and 100% biodegradable biopolymer composites. The material that we are using is developed in collaboration between us and the Danish Technical University, the Danish Polymer Center. And it combines collagen glue, which is a protein-based binder, with various waste-based resources which are locally available to us here in Denmark. So these include things like seagrass, bark and wood flour, cotton sourced from clothes and linen. There's many of the, or almost anything actually, that we have been able to find has been tested through this material system. With the addition of water, with the addition of water, heat, and glycerol, this material takes on a thermoplastic-like behavior, which is something that's quite rare for biopolymers. And this means that we can heat that material up, we can disperse fibers and fillers into it, and then we can 3D print it using a heated extrusion system. Once those prints have cooled and dried, then they take on, or they gain the properties of strength and stiffness that makes them well suited perhaps to non-structural architectural objects such as panels or cladding systems. So a key aspect of the material system is that the types and the ratios of the fillers and fibers that we're putting in are variable and interchangeable. So we can dial things up and down. We can select and combine these constituent materials in different ways, depending on what's available, or to gain particular desired strength or stiffness properties, color or texture. And then also that this physical recipe space of grading is also then represented in an associated digital recipe space, which connects material recipes to their various performance parameters. So rather than trying to hone in on one particular optimal recipe, which would be a fragile solution in a sort of dynamic resource context, what we are trying to do with this material recipe and its paired material recipe space is to create a flexible solution space that could be searched, extended, adjusted in response to changing material availabilities. So in a sense, it's to set up a kind of safety net. So if not one resource is available, this is a tool that would allow you to find quickly a suitable substitute that is. And we've been developing different demonstrators that start to connect the breadth of that recipe space to the design of architectural panels. The first of these explores a retrofitted interior paneling system. It's actually in the rear wall of the exhibition behind us here. But here we have a generative algorithm that's responding to an existing wall by creating porous panels that includes connection points, structural paths, and non-structural infill areas. So in this case, materials are sampled from that recipe space for their structural properties, where several alternative materials are actually used, where similar properties are found. And then we also sample that material space to achieve a stepped color gradient through the infill areas of the panels as they move up the height of the wall. And here you see the two sets of specifications that inform each of those panels, and then their combination within single consolidated printed panels. A second approach, I'll just get the clicker working. A second approach is to connect multiple streams, multiple material streams at the nodal. So instead of creating pleated graded structures, as in the first demonstrator, to be able to grade continuously through these panel elements and achieve a continuous graded blending. So in this case, the specification does not need to be disconnected samples from that recipe space, but can actually be taken as a continuous walk along a contour through that solution space that connects changes and variations in the material recipe and maps them onto particular points of a print path. Here are some examples of some of the graded panels, which are also exhibited in the exhibition behind us. And the ideas geometries here are connected to prototypical development of an exterior weather screen use case. So beyond the initial making of the objects, and also slightly beyond what's described in the article, it's also important to say that there's another wrapper around the research that focuses on how we can cascade and reuse this material. So how we can give it a long life by strategically activating the same thermoplastic-like behaviors as we use when we initially print the material. So at a sort of lower level of that cascade, we're able to reapply heat and water and perhaps top up with some glycerol to be able to melt down and reuse exactly the same material ingredients, whether if they're as a print mistake or as a panel that can become another object. Beyond that, though, we're also able to start and have started prototyping some of these higher levels of circularity. So systems that have been printed and designed for one specific location, we're able to geometrically adapt them, bend them into shape so that they can be installed and fitted into a second location. And here, our project Radicant is reimagined as Ready Bent, which is what is installed installed on the back wall. And then lastly, damages can also be addressed through maintenance operations and repair, which are based on conformal printing strategies that activate the material's self-adhesion. And some extremely interesting PhD research by one of our PhDs, Andrea, pushing these forwards. So I think I'm pretty much out of time, but to summarize and conclude, I think the article really is asking how the prototyping of waste-based biopolymer composites can start to open up new models of circularity, and reuse in architecture. And our argument is that for these to be flexible and robust, they need to be grounded in an appreciation of material availability and accessibility at a local level, and particularly in the case of bio-based resources and waste-based bio-based resources. And then I think we also hope that in these prototypical panel designs that we've also been able to show the potential for how those graded recipe spaces can be connected and activated through architectural design in the design of graded panels. Thanks very much for your attention.
Thank you, Paul, for the wonderful presentation and for touching upon not only the technical aspects, but also the societal aspects and how we might view different streams or different points. I'm sorry. Our next speaker, I didn't know if I needed to know something that I didn't. Our next speaker is Tom Svilans. He is also from here, from CETA, from the Royal Danish Academy, and he focuses a lot of the work on wood. So, thank you.
Can't tell if it's on. Yeah. Okay. Hi everyone. First of all, it's really nice to be here. I'm super happy to present this project for you. So on behalf of myself and the rest of the project team, I'm very happy to present our project, the Marina Spa prototype, today. The project brings together an interdisciplinary and actually quite geographically dispersed team of professionals and academics. It was initiated and led by Norwegian architects Helen and Hard, Siv Helene Stangeland, Håvard Auckland, Simon Eischermann, and Reinhard Kropf. It involved 2 academic partners here in Denmark, so myself from the Royal Danish Academy, and Niels Martin Larsen, Anders Kruse Aagaard, and Mathias Haraldsson from the Aarhus School of Architecture. It was guided and managed by Martin Antemann from Design to Production in Switzerland. Engineering advice was contributed by Herman Blumer and Christoph Meyer at Creation Holtz. And then finally, the bulk of the fabrication and the delivery of the project was done by Morten Winter and his team at Winter AS here in Denmark. So today I want to give a brief overview of the context of the project, describe a little bit how it was resolved through a digital modeling approach, and then focus on the 2 main resource streams that make up the project. So crooked oak logs, and reclaimed timber from the production of flooring. And describe a little bit about how these were leveraged to create the final piece that we just saw. Yeah, so to provide a little bit of context, in late 2021, Siv was invited to participate in the exhibition Women in Architecture at the Danish Architecture Center here in Copenhagen. That was with the opening date only a few months later in the spring of 2022. So the intent was to exhibit a timber pavilion that would be designed and built specifically for the exhibition. This gave a timeline of roughly 5 months from the project initiation to delivery and a budget of roughly 25,000 euros, which therefore set the mood of the project, which was fast-paced and with a limited budget. So from this initial point, a team was assembled through various networks of people, all knowing each other from some previous experience. And the key thing that we also talk about in the chapter is that an element of trust here was important, since the team operated without contracts or kind of hierarchical roles, instead sharing the goal of achieving the best possible result. So from the very beginning, the whole team was engaged, working very closely together to confront and resolve problems in a kind of roundtable discussion or roundtable format. The project itself was derived from an earlier unbuilt project done by Helen and Hard for this kind of enveloping, nurturing spa space. And the design features a lattice structure that is made up of curved timber elements, which forms this overarching surface, formed out of this kind of reciprocal timber structure at the top and is supported by 2 rows of what we call the V columns at the bottom. And in between the V columns, there was this idea for seats and areas of rest and spaces for contemplation. So very quickly, the first discussions revolved around the problem of how these elements could be produced and connected, trying to avoid complex double curved geometries that would require very intensive production techniques and trying to avoid non-wood connectors or extra elements. So the vision was to do it entirely out of wood. The discussion drew from the previous and ongoing research and experience of the academic partners, which also helped in prototyping alternative solutions and brainstorming how this could be accomplished given the involved know-how. So the project employed a fully digital delivery in the sense that there was a digital model at the core of the project that was the central source of information for its realization. And this was slowly built up in levels of detail in the kind of well-established method of using a master surface that's populated with center lines, which was then informing the volumes of the beams and therefore generating the element geometries. The next big challenge was how to resolve all the many connections without any steel connectors such as plates or screws. So from the approximately 130 unique elements, there were about 120 unique joint conditions with no real repeating situations because every joint was slightly different in some way. So therefore the topology of the model had to be analyzed to find similar joining conditions and develop a kind of a family of different joint types that were further specified and adjusted for particular edge cases or particular situations. This was solved in a modular way and through lots of roundtable discussions from the architects and the fabricators and everybody involved to resolve exactly how this would happen, how the geometries would be resolved, and how we could combine the knowledge to solve these joint conditions. Yeah, so the whole discussion about resolving the joints took place in plenum with everybody's comments integrated into a series of discussions. So here you see the main components of the structure, beginning with the sill, beams, portal frames, the flooring, the V-columns, and then finally the reciprocal structure. And then the final family of about 9 different joint types, each individually also variated depending on where it was in the structure, what kind of particular conditions were different, and where it lay. Yeah. So the material waste streams. The first one I wanted to focus on was this. Whoops. Yeah. Crooked oak logs, which are ordinarily discarded by the sawmills and used for firewood. And it leveraged ongoing research at the Aarhus Architecture School in how digital scanning and fabrication processes can enable better usage of such non-standard timber and its natural forms. The team at Aarhus used this research to collect, scan, and assess oak members that would be used to create the seats. The design of the oak seats was therefore broken down and allocated to specific timber boards, taking into account the presence of features and defects in the natural oak forms. So the final oak, the oak was assembled and CNC machined into its final expressive form. And here are the finished seats sitting in the context. And this is the second space of production, the workshop at Winter, where the rest of the production of the beams and all the elements took place. The second material stream used offcuts from a wood flooring company, Dinesen, here in Denmark again, to compose the main beam elements of the structure. Now the problem from the outset was how to create curved elements in a simpler way. Since glue laminating lamellas would require jigs and pressing equipment and quite complex infrastructure, it would be also quite expensive. Instead, a technique developed by Winter for creating curved doorways and window frames was introduced. So this had the benefit of being able to work with small pieces of wood and without the complexities of bending wood into curved shapes. It is kind of a small tiling of different segments into a larger form that can be much better controlled and glued simpler. Yeah. So as a production technique, it simplified the process, albeit with extra machining and assembly work. At the same time, however, it introduced more demands on the digital modeling side. So now for each of the 130 elements, all the different segments were also required for the machining of the individual segments that would make up each beam element. An extra step was then also needed, so matching each segment of each piece with the odd-sized offcuts from the waste wood in the best way to make sure, or to make the best use of the material, both in terms of form as well as in terms of looks and aesthetics. So here are the finished blanks, made up of several different layers, and being placed on the machine. So translating the model geometries and the different joint types required a very close collaboration between fabrication and modeling. Parameters for individual joints were defined, and then the values for these were extracted from the model and fed into the machining program. So we started with the easy ones to make sure we could keep moving, and then we solved the harder ones as we figured things out, always trying to keep one step ahead of the game to ensure that we made it on time. And not having such a tight and communicative team would have made such a process extremely difficult. So having this kind of close assembly of the team and being able to directly talk with all the other members of the team and work in the same space and constantly discuss things was an incredible asset here. Yes. So the joints were assembled with plywood plates and oak dowels, which also had to be accounted for in the detail model. These were also a mixture of digital production processes and some manual finishing work, as you see here. Yep, some more pictures of the plates. Again, each plate being different depending on where it was in the structure and what joint it was actually connecting. So in the end, the elements were successfully machined, and most importantly, they fit. We had this kind of worry at one point that if we assembled the entire thing, it would be upside down, but that didn't happen, luckily. Because of the fast pace of the project, there wasn't time to do mock-ups or pre-assemblies or tests, so it was all relying on the skill of each individual team member and their expertise. So some of the close-ups from production. Some of the joists, which are never seen because they're underneath the floor, yet also represent a sizable complexity in manufacturing. Some more details. And I think the last pieces left the machine very early in the morning on the day of assembly. So as I said before, there was no time for tests, and this great risk obviously added to the stress. But then for us was a demonstration also how, if that's possible, it's only really possible through this very integrated and agile team. And then finally, the effort in the thorough team discussions, the modeling, the planning, the detailing, all paid off during the assembly process. So there's not too much to say other than it went as smoothly as we could have hoped. The assembly time was actually shorter than anticipated and was accomplished with a small team of skilled people. Everything clicked together with the plywood plates and dowels, such as this. And this is probably my favorite moment in the entire project. So the simple slotting and clicking together of a plate actually represents everything that led up to it. So the entire modeling approach, down from the broad geometry down to the fine details and the tolerances in the joints. So much of the shared knowledge between the team members and the kind of dedication to crafting a high quality result that was shared by the team. So for me, all of that is kind of embodied in this very sort of simple and momentous event of the sliding of the plate into the joint that fits. Yeah, and here's some photos then of the final piece. So you see the similarity to the original rendering, albeit at a smaller scale, with the carved oak seats and a projection of the sea, unfortunately. One of the more complicated joints that actually has a very complicated internal geometry so that the edges align due to the way that the beams come together in this point. Some more joint conditions there. The insertion of crystals at the top to diffuse some light and create, again, this kind of calming ambience that's reminiscent of the original design. And again, the seats. So to conclude, the pavilion was made from material that in some respect either had been at the end of its life or otherwise had never been part of the world of construction. It was built with the intention that would also be deconstructed. And so after the exhibition at the Danish Architecture Center, it found a new home for some months here at the Academy in the library just next door. This demonstrated the feasibility and worth of working with wood in this way. So geometrically complex elements, joined with only wood connectors, made possible by a distributed and interdisciplinary team with a shared goal. And from a material point of view, to us it also showed the hidden potential in the vast streams of discarded or abandoned materials, how even from offcuts and crooked pieces of wood, something special can, in the end, be made. So also from a personal side, I just want to also thank the rest of the team for this incredible experience, and I want to thank you all for listening. Thanks.
Thank you, Tom. It is really wonderful to see how something seemingly simple can be actually very elegant, and it hinges on having quite a lot of complexity being taken up into detailing and making that work perfectly in an interdisciplinary team. And if that doesn't work, then probably nothing works. And it's very beautiful to see how it did work. Our last speaker for this session, I understood very late, are actually three, so I will be able to introduce one, because it is Andrea Rossi, and I would ask you to introduce your two colleagues that are joining, who is a research associate at the University of Kassel, and they will be talking about mycelium composites.
Yeah, so hi everyone, it's just very exciting to be here. As mentioned, my name is Andrea Rossi, and I'm here with my colleagues Nadja Nolte and Özdemir. And the project that we want to present, that is called Upscaling Mycelium-Based Composites, is a collaboration project between our team at the University of Kassel, the engineering firm Arup, and the Professorship for Design and Sustainable Building at the Karlsruhe Institute of Technology. And the motivation for this research comes from the realization that interior fit-outs in commercial and office buildings have a huge CO2 impact on their production, particularly when we look not only at the production of the building in its first instance, but at all the cycles of refurbishment that a building goes through. The impact of refurbishing an interior building is incredibly high. And partition walls, in particularly non-structural partition walls, are usually produced using materials such as gypsum walls, which are highly unsustainable materials that can get discarded extremely fast. And in recent years, mycelium-based composites emerged as new materials that can be used to replace a lot of these more unsustainable materials for a variety of indoor applications. These materials are cultivated on a different kind of agricultural waste, using fungi as binders to join these ones into a material which has a variety of suitable properties for architectural construction. What is the challenge? The challenge is that at the current stage, mycelium-based composites are unable to reach the structural dimensions that we need for panels for partition walls. So it's very hard to make a 3-meter mycelium panel because it has relatively low tension and bending resistance. For this reason, we propose two strategies to address this. And the first strategy deals with fragmentation, so with the process of reducing a larger wall element into smaller parts while maintaining the structural integrity to kinematic interlocking. And the second one, which instead translates a logic that we all know very well from reinforced concrete, and we worked on adding a tension reinforcement made of wound veneer inside the mycelium composites in order to allow much larger spans. As mentioned, the first strategy deals with fragmentation and how we can divide up a large element into smaller ones while maintaining structural integrity. To do that, we rely on the concept of topological interlocking, which are a class of structural systems that are based on kinematically interlocking elements that can be combined in structures that support transfer loads in multiple directions. In order to do that, we rely on the fact that in these patterns, we always have for each element, we have 3 elements that are supported by the element itself, and 3 other elements that act as support for it. So when we kind of repeat this pattern over a larger structure, we actually end up, and we lock it at the ends, we end up with a structure that is able to transfer loads. However, in order to do that, we need precise interfaces. Now, mycelium is not known to be a material which has high precision. Their production process has all kind of these uniformities, and we have like a lot of shrinkage in the material, so it's very hard to produce precise blocks. For this reason, we developed a process where we combine mycelium composites with an additive manufactured lost formwork, which is produced using bioplastics infused with wood particles that we can then use to cultivate these blocks. And so we end up with a mycelium composite where we have from one side the mycelium internally that provides the stability to the block, and on the outside we have a precise 3D printed shell that allows the blocks to properly interlock and transfer loads. Unfortunately, or actually fortunately partly, we had a very strong bond created between the outer shell and the mycelium composite. That means that despite its stability, we still got a certain amount of shrinkage happening, and also due to the fact that we have several people filling the blocks and everybody had a different idea what a filled block means, we end up with having a certain level of ununiform shrinkage. However, what we could do is we could tune the interlocking detail in order to ensure that despite the shrinkage that we could expect, the interlocking would still work and would still transfer the loads. So the resulting system is composed of around 100 blocks that compose a 2.40 m wall. And what is interesting is that these blocks are held together exclusively by the outer timber frame. And so by removing the frame, we are able to fully disassemble this wall and reuse it into a different structure. What is also interesting is that since the kinematical interlocking works in any direction, we are able to reuse the same blocks not only for a vertical wall, but potentially also for a horizontal hanging ceiling. And moreover, what's interesting is that at the end of life, the material, the whole block can be broken up and shredded, and the material itself can be reused as a substrate for a next cycle of production with a reuse amount of up to 40%.
So the second strategy that we want to present to you today is, as mentioned, the strategy of internal reinforcement, which aims at allowing to produce larger elements in a single piece, which is obviously desirable for their application in construction. And the reinforcement is based on a wood veneer lattice that is integrated in the mycelium substrate matrix before the growing process. So during the growing process, the mycelium network can bind to the wood veneer lattice, and this can realize a reinforced component. We developed this strategy based on previous research, which has identified that the fundamental limits to the application of mycelium-based composites for large-scale architectural components are based on, as mentioned, poor tension and bending resistance properties. And the low tensile strength is largely due to the lack of longitudinal elements that can then transfer the loads across the component. So our process is relying on a 6-axis robot and a custom-made end effector, which allows the extrusion of the veneer strips in selected location, cut them and bind them together to already placed strips. The lattices were manufactured from thin edge-bending rolls of maple wood veneer, which introduce the long fibers into the composite that can be oriented according to the stresses in the geometry. The long fibers, they act as a reinforcement such as they do in traditional high-performance composites such as steel-reinforced concrete, and also they perform as a natural scaffolding for the mycelium growth. A key challenge during our development was the identification of a bio-based binding method that would keep up with the process speed. Most bio-based binders either require long curing times or they require to coat the veneer completely in the binder, which would negatively influence the veneer mycelium bond strength. Hence, we avoided using any binder and we introduced an ultrasonic welding process, which is usually applied to thermoplastics, and it is economical and automated and well suited for mass production. The ultrasonic welding uses a titanium horn that vibrates at high frequencies while being pressed on the material. And the kinetic energy is then transformed into thermal energy, which melts the lignin which occurs naturally in the wood veneer and binds the strips together in the fraction of a second.
And we did some tensile testing and demonstrated that these bonds are actually more stronger than the veneer itself. And so we proved that this is a suitable method for the production of the veneer lattices. Later on, we filled the lattices with a mycelium substrate. And within 1 to 2 weeks of cultivation in a controlled environment, the lattices were grown together with the mycelium substrate, creating the stable composite.
Thanks to the veneer lattice fabrication method that we've developed, we made a full-scale partition wall that has a uniform lattice embedded in. This lattice is connected to an outer frame, as mentioned before, that increases stability and improves the bending and tension resistance of the composite. We then wanted to see the design possibilities this lattice offers and produced a curved lattice. This single curved prototype was achieved by varying the distances between the veneer strips on the top and the bottom of the lattice. And to do that, we first designed the target geometry, and then we unrolled the lattice strips and welded them together to reach the desired curvature. Since modifying one parameter changes the geometry significantly, we went further ahead and decided to explore customizing the lattice cells, again attached to a wooden frame. Using structural analyses based on the requirements of a partition wall, we generated a lattice with 2 different cell sizes, and we used more veneer strips where we have higher stresses. We then took the cell sizes as a guide to reflect the inner reinforcement structure on the surface design. A wooden mold was used to add relief and texture to one side of the wall and to achieve acoustic benefits resulting from the surface design. Following the production of the lattice and the mold, we added mycelium and let it grow for about 2 weeks. Here you can see the final outcome. We produced a custom reinforced bio-based mycelium composite with a surface design depicting the inner reinforcement structure. Our preliminary results have shown that the lattice and surface design correlation has an impact on the acoustic performance, potentially an opportunity to do acoustic performance tuning in the future. So this is a point we'll explore more in depth in the next steps of the research. And through a series of tests, we validated the increased performance of the composite with the integration of the veneer reinforcement. Therefore, this opens up a new range of applicability for mycelium composites. And as an additional proof of concept, we decided to put the project team on the wall, because why not? Now we'll see a video showing the whole production process from the beginning until the end. So we start the production by laying the veneer strips with a robot arm for first producing the 2D grids. Here you can see the simultaneous production of the mold. And then we add the waves that create depth, connect the top and bottom 2D grids, and also improve the shear resistance of the composite. All the veneer strips are connected with ultrasonic welding without using any adhesives. And we start preparing the inoculated substrate by eliminating the clumps as much as possible for filling. And here we're putting the material manually on the mold and in between the reinforcement lattice. Now everything is ready, and the mycelium is left to grow over the course of 2 weeks in a controlled environment. here you can see the mycelium growth time-lapse, where mycelium is expanding its dense network and connecting the substrate particles together. And at the end, we get a dry composite, and we actually installed it in our office to demonstrate its use as a partition wall. The entire project team. So the next steps of our research are extending our production method to achieve double-curved, large-scale, complex mycelium-based composites. We'd also like to achieve functionally graded elements using different kinds of substrates in one component. And we're exploring the lattice and surface design relationships effect on the acoustic performance. And lastly, automating the fabrication of mycelium composites even further. And with that, we're concluding our presentation and looking forward to your questions. Thank you.
Thank you very no, but please stay with us. Thank you very much for the presentation. It is really nice to see this contrast between really high tech and very live material that you end up putting together, and how that brings you to new challenges. And I think that this is something that is quite shared amongst all the presentations. So I would like to invite all of our speakers for the session, including our keynote speakers, Anders, to join us on stage for the panel discussion. And you may take a seat over there. Do I have a seat? Okay, I'm staying. No, I'm all right. I'll feel like the interrogator from up here, but it's. But it's only fair because it gives you center stage, and I'll fall into the background as I let the audience actually probably ask most of the questions of you. But before I do that, what I wanted to highlight are a few things that I've kind of picked up from having these beautiful presentations all together, because even though they deal with very different materials and perhaps very different types of projects and very different ambitions, at core they are very similar, as in you all try your very best and succeed quite well to deal with effective use of material and effective use of a particular material, and trying to coax out the qualities of a material that is actually unknown into doing what we want it to do. So that was put quite nicely by Paul as well, that it brings up a question of flexibility and robustness, because when we start trying to bridge this dichotomous relationship between having a very precise process and at the same time a very imprecise material, it really challenges us to look at how things could be built and reframe also our understanding of a building, what it might be, what kind of performance we expect from it, and how we might reuse it. So one of the questions that I had, and then I'll let the audience go on for that, for most of the projects, is how do you reconcile this very high precise technology with an imprecise material, and what that might mean in how we need to reframe our understanding of durability, for example, or what we expect from our buildings?
Well, I could maybe start with an answer from our perspective. I mean, I think for us, it has started as a I think, with several distinct areas where we've really had to work out how actually to run some of these various materials through some of these production processes. So particularly, I mean, the idea of taking a heated material with variable viscosity through an extrusion system with precision is difficult. combining multiple of those materials, which might have multiple viscosities, is also difficult. Understanding how those materials start to behave as they dry, how they change shape. I think this is something that was common to many of the projects. I think this is one level of that question. I think the surprise for us has also been that all of those uncertainties also extend into the in-situ behavior of the materials as well. And we have also needed to try to track and record and understand variability and behavior with our panels out in the world, whether they're inside or outside, they are responding. I mean, unless we fully coat them and seal them off from their environments, they're responding to relative humidity as timber would, actually, or as wood. And their technology, particularly sensing and registration technologies, are also a key part of trying to understand how to bridge between those worlds. But I would say from our perspective, it's very much work in progress. We are not, I think we're on the way, and that is through making predictive models, building up data sets, building up catalogs of behavior, and trying to create mappings based on experiments, based on the makings of prototypes, and tracking their behavior so that we can cycle that back to the technical side, which is the production or the installation or the design of detail, fixings and details and connections.
All right.
Yeah, just from a wood side, I always find it fascinating that it's such an old and well-used material, but we're still finding new ways to kind of squeeze more potential out of it. And I think from some of the stuff that we explored, and also some of the stuff we're doing here in research, in using digital tools for sensing and scanning and finding out more about it, it's kind of unlocking new potentials for how we could use things such as discarded waste materials or reclaimed timber from old buildings or natural forms in a new way. And I think that's a kind of key application of technology that I see as very interesting in the world of wood. Because I think we can make very precise geometries, we can cut all sorts of things. We still sometimes get kind of hamstrung by just the behavior of wood, and I think helping to understand that, or kind of finding tools or techniques that we can kind of dissect what the wood is doing at a more precise level, I think is really interesting.
Mm-hmm. Yeah. That also brings it a little bit,
Yeah, I mean, I guess from our side, I think that's something very interesting from the way we work, in the fact that there's always this tension between like a very kind of high-tech approach to the fabrication, and from the other side, a very low-tech material as mycelium. I mean, Adrian Rigobello, the researcher here at CITA, uses to say that it's easier to grow mycelium than to make bread. So there's a little bit this interesting interplay of kind of finding where is the line of what makes sense and what doesn't, because from one side, much higher technologies can allow us to, of course, industrialize and make these materials much more repeatable and reliable. But at the same time, the possibilities of lower technologies are open up also the possibilities of having like much smaller scale, much more localized production processes. And so for us, it's just very interesting to kind of really be at that interface and try to kind of poke a little bit on both sides of the divide and try to understand where makes sense, what makes sense where, so to say.
Just want to add something from the mycelium perspective, especially when we talk about durability. I mean, there's always this balance between durability and biocompostability, and one of the questions that we get is that how long does it last? And when we were looking at our project, like we decided to make partition walls that have a lifespan of like 7-8 years. And of course, it's impossible to expect the same performance from this material as the concrete, for example. That's why, as Andrea said, like what makes sense where exactly, how we're going to use these materials as which building elements is quite, I think, important. And also the industry expectations probably also should be adapted according to these new and natural materials.
Maybe on the imperfection question. I mean, and for our project, for the scale of the project, and also because it's a discrete structure, so of course imperfections are there. You cannot do really much about it, even if you are super precise with the printing and production, assembly. There are many unknown there. But the strategy we adopted was to design for tolerances. So we knew that they're gonna be there at the end. So that's why we changed, for example, our assembly strategy in order to deal with this potential imperfection and gaps that you can encounter at the end of the assembly sequence of the project. And let's say by controlling the shape of your structure and knowing the behavior of masonry, you kind of control these imperfections. So even if they are there, more or less we know how the structure is going to behave as well with imperfections.
It would be safe to say that actually what we'd want to do is move away from the being incredibly precise and accept some imprecision if we really want to go this route, right? So maybe a question that would go more towards you, Andres, is then how do we get all the stakeholders or the value chain to accept that? Because we are used to, and it's not necessarily a discussion about norms, but generally in approaching it.
Yeah, I mean, first of all, I'm super disappointed that I'm the only one that doesn't have a robot, apparently. So I have to get up to date there. But I mean, it's super inspiring to see these materials. I obviously know a lot of them, and also the processes that you're working with, which is super inspiring. And I'm just sitting with basically all of these methodologies and thinking that the part of something of the boring things that we are trying to incorporate, fire, all the boring buildings legislations, data, is where this jumps from, what you're sitting with here and what I've spent 3 years on a project, try to show that, because then I'm allowed to build with it. And I think with all this fantastic research that you have, I mean, everyone can see the potential. But the potential of leaping from these either complex shapes or complex manufacturing, where they're informed with the answers or the need to answer some questions out there. And that's why I'm also saying that the circular buildings legislation needs to be invented, but these type of products need to answer to that. And I think it's all there. It's the data, and you're so good at handling these complex things. That's why it's easy for you to produce complex shapes as well, which is not even needed because it's interesting anyways. But you also do that. So I think like everything's ready there. It needs to be lined up and informed with the things that are so important to compete with what we otherwise are using on the other side, building buildings. And so, yeah, I think that's, I call my products advanced low-tech, because compared to this, they are super low-tech, but they're advanced in actually getting them realized. And I think this is super advanced, and the low-tech part is actually getting them scaled.
But like you said, like that's often dependent on standards and regulations, which can be changed over time through effort. I know that, for example, in Norway, the whole integration of reclaimed timber into the building industry is progressing, which would then hopefully open up more and more possibilities to kind of transfer over to that side, or to the construction side with alternative materials. Exactly. So I think it's promising.
Yeah.
Yeah.
All right. I think we have a very large and interested audience, so I would open up the floor for anybody who has a question. I see hands going up already. Do we have a microphone I can give around, or somebody can give around? Okay.
Thanks very much. Dominic Holzer, University of Melbourne. I have a question for Anders, and that is, with the model you described, with the new circular economy, are we likely going to see a massive change in the supply chain, where we're going to see let's say second-hand warehouses like Salvation Army type, but for builders and architects, warehouses for repurposed materials? Because obviously at the moment the materials we use are predominantly from fabricators and suppliers and distributors. Within the circular economy we will probably need much more than that.
Yes. It's a good question. I think obviously we need these materials and these fractions to be present. I see a great movement in Europe of new companies that are registering and collecting these materials. So the past 10 years it's moved from being very difficult to access waste fractions in large quantities to them being identified. The problem is that they're still a waste fraction if you haven't put them through these innovation processes that you're also showing, so they become from waste to a product. So the problem is not finding the resources and the amounts. The problem is that no one has invented them far enough for them to be competitive products. That's the part of the equation that is missing. So that's why I'm always encouraging that to scale it. Waste fractions of wood, it's out there, lots of it. But the part of making it a viable material to build large entities and large structures with, that's the part missing. And yeah, I hope that answers it a little bit.
There's somebody right up front.
My question is for the mycelium group, and thank you guys. Dealing with mycelium is a very delicate process in terms of asepsis, no? So how did you deal with the process of contamination? Because it's very difficult to achieve non-contaminated block. No? So how did you deal with this process of cleaning manufacturing?
So the thing is that when we filled these structures, we used already pre-grown materials. That means that the time that we unpack it, the mycelium has already grown through the substrate, which makes it be stronger against any contaminants. So the requirements on cleanliness were not so high. So I think that's also how you would do it industrialized, that the first process where you need to be really clean, sterile, let's say, is separated from the actual filling process or scaling up process, let's say.
Thank you.
Yeah, the suits and masks are more for cinematic effect than the other two walls. We didn't wear anything. They grew perfectly well too.
Good communication.
I have a question about Phoenix Bridge. As I understood, some of the components were slightly curved, and since it's like printing in parallel, how it was achieved, like inner and outer radiuses were different? Like,
you mean the different angle between start and end plane, or the different layer height?
like different angles between like layers in one component. So
by reducing the layer height in the same layer. So, and then by varying the speed of the printing, like usually you can control the speed or the flow rate, but usually it's easier to just control the speed of the printing, and then you, in the same layer, you have a different thickness, and then by accumulating this different thickness, you reach the tilted angle that you see at the top of the component.
Okay, thank you.
Hi, I'm Claudia from CETA, PhD student. I have a question that probably is open to all the panel. And I'm thinking about technological accessibility in the sense, you know, what's the threshold between complexity and doing for people? Because, I mean, as Andrea said, like, everybody has a robot here, but, you know, in the open world, the normal people don't have. So I'm thinking about, you know, the farmer that wants to have like a mycelium wall, but doesn't have a robot. So how would you rethink your practice, or maybe adapt to this more, you know, local or normal people, you know, that wants to actually be open to new material, to different type of fabrication that is just not the common one that we have.
I sometimes think about that in the context of what it's difficult to, like, we're dealing with high technologies, CNC machines and scanning and all that kind of complicated stuff, but sometimes I think of it as like, we have incredible complexity in our phones as well, but we don't need to understand every single thing that's going on inside of the phones to be able to use them effectively, right? And I've been trying to think of like, what is the analog of that in the wood world, and it could be, yeah. I mean, we see that in the rise of desktop 3D printers that are now just kind of, you know, take a scan with your phone and press play, and that kind of, most people can do that. I just don't know what the analog in the kind of wood industry would be for that, but I think there must be something like that. Yeah, that's my thought on that.
Yeah, I mean, from our side, I think that the process that we demonstrated, of course, when it's done with an industrial robot, has a lot of advantages in terms of speed, reliability, and so on. But there aren't really significant obstacles to kind of doing that same process by hand. We actually did several samples, like entirely by hand. The ultrasonic welding process is one of the reasons why we use it. Is not just because it's really effective for the process, but it's also not an particularly expensive or complex technology. It can actually also be done by hand, so we have just a gun with the same sonotrode mounted on that, and we can use that very easily to kind of weld wood by hand. So imagining that combined with some more accessible technologies, like for example augmented reality, or even simply measuring out the wood strips and putting them together, of course increases the time that is required to do that, but it all of a sudden like lowers the technological accessibility significantly.
I think, I mean, just also, I just wanted to say, I think it's also possible to push back on that idea that just because something goes local out into the community, it needs to be very simple. The Fab Lab movement has shown that, you know, that technologies can go out into the community. The idea of the phone or the configurator. I think these things are not in tension with one another necessarily, but they require some kind of organizational system or some kind of infrastructure that enables it to happen. Sorry.
I was going to say almost the exact same thing, but actually to ask kind of, does everybody need to build as well? Like that's why we have people that build and do all these other kind of things, right? And if you look at like, it takes time to be trained in a craft, for example, as well, thinking of woodcraft. But to kind of flip that around is this, I don't know, it's maybe a can of worms as well, but to ask if everybody should be, if everything should be accessible to everybody, or kind of if everything should be kind of opened up to everybody. I think, I don't know. I didn't think that went through, yeah. Absolutely, yeah. Yeah.
I want to know what's going on.
Yeah.
I feel like sometimes there's a bit of discrepancy between what we're doing, what other, like the real world is doing. So I think it's just nice to have this accessibility of, as you said, it doesn't have to be in contrast, but maybe it's a collaboration, it's about community engagement too. So I'm just saying that, you know, maybe we can, I don't know. Yeah.
But there maybe it's also kind of spills over into kind of accessibility of training or education as well, right?
Yeah.
But there's two sides for sure. I mean, there's the industrial fabrication that has even way higher complexity than, I mean, the wood industry is very, very, very complex, and many of the other industries are super complex setups. So it's not the complexity, but where I see that something is way behind is when you then enter a building site. Then it's like you're going 100 years back.
At least.
And it's the same as it's always been. And the questions that you meet are the same, super conservative, nothing's possible if it's not the way that they've been taught the craft for hundreds of years. So I'm not saying that the craftsmen are not doable in this transition. I'm just saying that technology between building site and prefabrication is like two totally different ages. And there, for sure, there is some leaps that needs to be closed somehow or made for this to actually accelerate and be scaled, for sure.
I would argue that even on a professional level, that's needed, not only on the craftspeople level.
Yeah.
We have plenty in ourselves that resists that change somehow.
Absolutely, yeah.
But I also feel that like probably also in the way we work on all this project, I think we also have a similar approach. There are also kind of interesting lessons to be learned, because at the end of the day, nobody sitting here is a mechatronics engineer, I guess. And a lot of the tools and the processes that we see are actually relying on a lot of level of like a different type of craftsmanship. So like the tools we have are all built out of like laser cut plywood and 3D printed parts. But yeah, and so I think there's a lot of potential to kind of translate that back into like really not that much the process itself, but more the mindset of kind of looking at the process and finding ways to go around that based on the context in which we're at. And in this context as a robot, in another context that might not be a robot. And I think the mindset that is common to, I think, all the projects is really powerful to kind of solve those problems.
Mm.
Thank you. I've got a question, I think, for Anders, but maybe for all the panel. Nobody's really mentioned the information costs involved in this sort of work. Taking little bits of wood and finding which ones are going to fit into what place optimally. Any thoughts about what the new technologies, machine learning, artificial intelligence, and so on, are going to bring to this? It seems that there needs to be a fusion between fields here.
I just think it's interesting that they're starting to introduce the cost of data into things like LCA, or like the size of the data, and recognizing that it does have an energy impact, for example.
I think, I mean, it's also, I think, I mean, at least from the architectural practices that I talk to, an understanding of their data use and the impact of that in cost and carbon seems to be rising to, certainly in awareness. But I think, I mean, some insights there was that actually maybe it's not so much new AI models or these kinds of things that are causing those great data increases. It's just really normal architectural practice, which is having a 500 gig file, making a small tweak, and then calling it version 2, saving it, doing another thing again, version 3, and actually very rapidly accruing a huge amount of data in a practice around a project, which is not used. And not actually linked to any of the processes that might be about engaging with material variation or optimization. So I think that the data question in practice is really important, but it's much wider, I think, and broader than just some of the new technologies or the optimization or AI models.
You can say that the time optimization in my world with this is also for sure manpower building this part and this way of realizing these ideas in the extent. And I think the past years we've seen an incredible increase in material prices. And it has stopped development totally, which is in many ways a good thing. But what has been really intriguing is that materials that hasn't been on the market at all because they were way too expensive, Mycelium being one of them that we tried building with as well, all of a sudden these increased prices on normal materials reached a level of prices of what they should be costing. I mean, a cup of water is more expensive than a cup of concrete. So, I mean, that's where we are. And all of a sudden this increased. And that allowed new types of material into the market, and projects that we were doing at that time, we always get the question of how much they have to pay more for our materials and this way of thinking. And here it was a stable economy. So I know I'm answering a little bit different than my colleagues here, but I think economy and time is something that is changing kind of like stock markets in the way we develop, and all of a sudden allowing new types of material to enter our industries.
Thank you for your presentation. There's clearly a lot of skilled and knowledge on that stage. One thing that stuck with me from the first presentation was the word risk. You're all kind of a bit of risk takers, picking up a project for 5 months, timeline, or building with materials that haven't been used. How do you foster interaction with other industries or other people who are less risk averse? How we build the bridge to reach those people and reach further out than us here who are already convinced? How do we convince further people and further industries?
In the case of the bridge we built, for example, we integrated all the knowledge together from day zero. So, I mean, of course, you have a risk because you are working with a not regulated structural material like 3D printing, but combining, let's say, structural knowledge, material properties, the technicians developing the material as well. So you build up, let's say, this trust in the structure, and you control in a systematic way what you are doing with all the experts sitting at the table in an integrated approach. So this is how we maybe deal with risk, by trying to control and think about every step we take in the design.
But I think it's interesting because I think also there are producers of buildings that do not want to take any risk and are totally happy doing very non-risky stuff, amazing. And then there are others obviously that do take risks. And I'm not sure if you can, like, how to encourage people to take risks if there's no incentives is also kind of a question. I think one is by demonstrating that, like, with a bit of risk, the rewards are much greater than not taking the risk. I think that would be the more kind of readily applicable kind of answer to that. But there's also the reality of this, just some actors do not take risks or don't want to kind of do anything riskier, and then you're then you can't do anything about it, I guess.
I mean, for me, I think I said some of the things, but risk in the building industry is converted to economy and budgets. So if you're afraid of something, you just increase the price for it, and then you can do it. So what we have to do is exactly what you're saying. We have to both show what risk is, and then show the reward. So I would really agree. I think what we always try to show our clients is the reward of doing this. If they build like everyone else, they're just throwing themselves into the red ocean of similar buildings and architecture. And they survive for sure, but there are clients that needs and wants to do something differently. And I think I introduced Mycelium to our client doing our 80-meter high wood high-rise. And that was the first time I saw fear in his eyes. So you want me to build fungus into my wood house? And he had no knowledge about that it's not the same. But the race of knowledge behind these new technologies and materials are very far away from the realization of the buildings we see today. And so one thing is explaining the technologies, but it is also to find the rewards in why they should do it. And that's communication, and it's not greenwashing. It's communicating why it's worth more to do, so someone wants to live there, use it, encourage it, talk about it, and be proud about being in what we create for them. And that is the reward that we have when we succeed, that someone takes it over and make it grow.
Thank you very much. There are a few people behind. If you go just a little bit.
Hello. I would like to ask you a question. When we rely on CNC technology and glued wood technology to prefabricated wooden part, the form and curvature of this part are fixed. That is, this part can only be used for this project. Is this not environmentally friendly? Because when you no longer need this project, the part can only be distorted and cannot be used for other projects. Yeah.
Yeah, I mean, I think it's the kind of constant tension between something that is very specific and something that's generic. And if you take apart rectilinear old barn, you can use the elements for many different things because there are a lot of different things that use it. But I think it also is a question of how long it, or what do you reassemble it into, and the lifespan of that project. I agree, it's much more challenging to reuse very unique elements, but particularly with wood, there are options to remachine things or change the joints, or then also come up with new design methodologies that could actually integrate these existing forms, much the same way that, I mean, all the research that's happening with using these existing tree forms and how that can be integrated in design. I think you could apply the same mentality towards existing elements from curvilinear timber structures. So I think that would be the best kind of path with respect to that. Yeah, hope that answers the question.
Toronto. I found myself thrilled, on one hand, by the extraordinary transformative crafts based on distributed systems, based on extraordinary resilience and openness that was offered in this session. And it made me tremendously motivated to use and implement the new processes and the new economies that you're offering. And yet, with a question perhaps for Anders, but for everyone, I also found myself tremendously ambivalent when I thought about the slowness and the incrementalism and the lavish labor that is required for these approaches. Slowness perhaps is a virtue that we can speak of, but in the face of crisis, of emergency, of the necessity for central government and deep, rapid transformation and delivery, equivalent to wartime throughout the entire planet, let's say, it seems to me that we have a tremendous pushback against this kind of indigenous model that we're offering here, in this incrementalism, in the lavish, incremental, distributed topologies that are being offered here. How do you navigate that profound ambivalence in the necessity of centralization, of delivering something that's durable, that's radically cheap in the face of a swing to the right economies? How do you work back and forth between two seemingly very different economic models?
Thank you for that simple question, but quite good. I think with our line of work, speed is really difficult to define. I would say development takes such a long time. So what is speed? The necessity of the crisis and things we've known since the 70s, and nothing has actually accelerated or solutions have even been introduced. So talking about it on a geopolitical level, talking about war, talking about climate crisis, it is extremely demotivating to even move. So I think right now the most important thing is not to seek to despair, because that's what we're looking into. And therefore asking these questions, which is totally legitimate, but the answer is not to find or give up in this because it's too late. Because it's certainly not too late. But the fact and the matter is that we have a building industry that is leaning into an end-of-the-rope strategy where there are no materials, where there is not enough energy. The question is, where's the planet at that time when we reach that end? But our generation, at least me that are getting way too old to sit up here, probably, you guys are young, is to leave just a little bit of light out there for solutions that the next generation of architects can seek, implement, and scale. A lot of them won't work probably, but they are the ones that are finding solutions, kind of creating at least the CO2 reduction or the possibility of changing the building sector, which is 40% of the total emissions. So the war now in Ukraine and also in Palestine shows us how quickly we can demolish, and just as quickly we need to rebuild. And we are working in Ukraine and trying to find solutions for how to rebuild with this. And many of these things that we are talking about are the only solutions because there are no resources. So I see possibilities and are extremely positive that we actually sit with some things that can be scaled because the existing structure cannot solve these issues. But the political and the economic and the existing industry is fighting against, and they're good at it. It's been like that for ages.
We have time for one more question, perhaps, right?
A more positive one, maybe?
Ooh. And now everybody's courageous and puts their hands up.
Hello. Thank
We'll
you
take
all
the
for
other ones.
the wonderful presentations. I have a connected question relating to some of these conversations around risk. And I was wondering, from the perspective of your different projects, do you think that the conversation around risk can change? One thing that occurs to me is so much focus is placed on the risk of the solutions, the things that are being developed here and being presented. How do you manage this in terms of fire safety and so on and so forth? There is, of course, a risk associated with the status quo that I think could be discussed more and maybe could give a stronger argumentation for moving more in the direction that's being presented. Do you find that there's room for this type of conversation in the context of these projects? Would it be helpful to maybe have more initiatives to enumerate those risks of not doing anything? Or do you think it's already very well documented and understood? Certainly in this room, I think understood, but in the industry as a whole.
I can start maybe. I think a lot of these products and the industry is moving towards these things. It's not that we don't have the solutions right now. We talk about scalability and all these studies, but what needs to be done is a pressure on an industry of developers and economic pressure. And what we're seeing now is a taxonomy that we haven't talked that much about in this forum, but the taxonomy is it's a way of engaging and putting pressure on the stakeholders that are building, that they need to choose these solutions. And these things are coming. And so what we have in the industry is not answering to these demands in the taxonomy. And then you have a political discussion about where is the roof put on the pressure, how far can we go? We have the reduction roadmap, fantastic work that architects and engineers are doing here in Denmark. And those types of pressure that we need to go further is happening. Then that leads to Mycelium to be a product that has to solve fire, the concrete, the strength, and so on. And that's why these products and technologies are interesting more than ever. Maybe you would.
Yeah, I mean, for me, maybe also connecting a bit to the previous question, I think there's also this problem that we are not yet acting as if we are in an emergency. So we're kind of looking at all these solutions and we are expecting them to be perfect before we put them into reality. While instead we are accepting a lot of materials that are per se not perfect from a lot of perspectives. Concrete buildings get too hot and too cold. And we're fine with that. There's buildings that get built and they eventually leak. So I think there's also a need to kind of understand that we have that sense of emergency, and so that some of these materials are necessarily an experiment. And so there are certain levels of risk which we need to take because we just, as you was mentioned before, we just don't have time to kind of get them to the point in which they're absolutely perfect.
We have the very last question over here. No. Come back.
Yes, thank you for a very inspiring session. And I have to say that you, Anders Lendager, is kind of showing a path. I've been practicing for 25 years myself, and the building industry is what we have to kind of engage with. And I think your skill, or what you show, is a kind of agency and taking a role as an architect in a new way to deal with this big system that we have to challenge. And I think it's both a question, but it's also an honoring all of the attempts we make to find solutions, but also to maybe we need also to bring out our skill as architects when it comes to dealing with risk, because risk management is part of being creative, seeing potentials, making prototypes, testing, and being on an investigation path. And that's what we manage. It's part of our skill. So we have to also take that chance and take a new role in the system, which I think you're kind of showing us. But I would challenge you to say something about what are the, could you say something about the agencies that you believe architects should have in taking a front role?
Yeah. That's first of all, thank you, and I mean, that has probably been said the most times over history in this room. I think architects are the most important in this, but we really are. I think that the ability to use creativity, beauty, technology, and actually embrace that to create solutions in a space where there's no solution. That's what we're educated in. It might be that we need to do some things differently than we did in modernism and so on, but our capability, the definition of an architect is someone who can actually come up with some solutions where there is none, and make them doable, make them last, make them cultural and meaningful in the time where they are created. And therefore I think we're so important, but I also think that we forgot the strength of what we can do. I mean, I've been in many meetings doing buildings where the rest of the industry expect me to sit and say very little. Because that's what we do. We do a design, we leave it to someone else to build it. And then if we're lucky, we come back when it's finished. In that big gap of time, we don't really have a role. But in what we need to do now, and the way that we work with these materials, these questions, they are on us all the time. We're there at this last day, putting the last nail, window, whatever in the building. And we're part of that process. And I think the important thing here is that we fight back and get that power back, because that's where you control this transition. And it's few in the industry that want sustainability like we do. The other parts of the industry are chasing different parts, not that they don't want to be sustainable, but I'm just saying that we are doing this in a totally different way. There's something else that turns us on than just making profit. We want to do something good, and doing good now is doing sustainability. So we are extremely important, and we are also important on a political level. Politicians start to listen when they see that we can make it work in real life. Then they change their politics. I've seen it many times. So we are, as I see it, a very crucial role in this transition, and we should be even more. It should be more clear what role we can take, and not only be the one creating the designs, but take even more positions in society and push back, because that's where we can actually really change something. It was a very long answer. I'm sorry.
Well, good. Thank you very much for all the questions and all the answers. It was really an insightful conversation. I personally enjoyed it a lot. So I would invite you to thank our panelists one more time, and then we move on to the next part of the program.